All right, welcome to my webinar on how to use an Arduino or microcontroller to measure transducer preload voltage and convert it into megapascals. Um, why do we even want to do this at all? Like, why do we want to use a microcontroller? Why not use an electrometer or use, and what I showed in the last webinar, which is why don't you just use a modified multimeter or even the higher end multimeters, some of them, the benchtop ones, they have high input impedance voltage ranges for the lowest ADD setting. So why would you even want to do it this way? And there are so many reasons for that. And today, there's no slides. So for all of you who don't like slides, I have none for you today. So let's just go into the topic here. Um, so first I'm going to talk about the topic of this webinar is using, this is a bit more informal than before, using, and let me zoom in a little bit more, using an Arduino to measure preload voltage. And we know in order to do that, uh, this is make it wider, which I can't do that. Anyways, that's fine. In order to do that, we need a couple of things. We need high input impedance, and we need a sufficient voltage range, and also good resolution. Um, um, so all of these are necessary, and these can be achieved through the multimeter, as I showed last time, or electrometer. Um, you're also going to need that, the time constant, basically that capacitor for the time constant, and also reducing the voltage. Oh, yeah, so you're not seeing it. Okay, perfect. Thank you for letting me know. Yeah, yes, I'm not. I did not show the right thing. I'll just show this whiteboard now. Okay. Yeah, thanks for letting me know. So in order for yeah, thanks. So in order for to use an Arduino and measure preload voltage, we need high input impedance. We need sufficient voltage range. We need good resolution. We're probably going to add a capacitor and time constant. And the reason why you wouldn't use a a why not use, let me get this, why not use a multimeter, let's assume a multimeter or electrometer. First of all, that device may not have a high input impedance. So hopefully you can see everything now correctly. Yeah, so that device may not have a high input impedance, and also it doesn't convert the output convert output directly to megapascal. So the nice thing about having it on a directly from an Arduino is that we can write the code to convert the data, and we can do a lot. We can do as much, or we have full control over how the data is calculated. Now you could do this with a multimeter, then you hook it up to your computer, and then you have a separate program. But we don't really go, most people don't go through all those steps. They just assume a voltage. So typically, and a lot of times, I find that companies will just do like, the target voltage is 5 volts or something like, or 5 volts, or the target voltage is 1.006 volts, 5 volts, and that's gonna equate to like, I don't know, 50 megapascals or 40 megapascals or however amount they determine. So a lot of times when we talk about data, it's kind of abstracted because really we're not preloading to a voltage. That's not the point. We're preloading to a stress. So it's very useful to convert that to a value. And also the other thing is that it's very accessible. Accessible, so inexpensive. That is a benefit. You also have more control over electronics. Um, and there's just yeah, that's the any if you have anyone else has any other reasons, I'll read them out from the comments. But yeah, these are the reasons. It's just easier. You can convert directly into megapascals if you use a Arduino, and it's inexpensive. Like you can have your own display, you can have an LED, or you can have like, you could have like, basically you can connect like a relay for shorting, shorting the transducer. There's you can also put additional electronics to improve the time constant. There are a lot of there's a whole bunch of peripherals and things that you can naturally adapt. So now that we're all convinced that hey, it's a good idea to explore using a microcontroller to measure preload voltage, now what's the approach? So should we just connect the Arduino itself or the microcontroller itself directly to the capacitor? Oh, sorry, I had here like should we instead of having a multimeter here, and I can share this kind of a Microsoft whiteboard later. Should we just directly connect this to like the ground of the Arduino and like let's say analog 0 of and that why would that not work? You wouldn't want to connect it directly to the microcontroller because you only get a positive voltage range. You can only measure positive from ground, so you have to be like very careful about which way you're loading. The other thing is the resolution is all not that good. So usually either if it's a 3.3 volts microcontroller or it's a 5 volt volt multi microcontroller, you're going to have 8 bits or maybe 16 bits, and I know, or 12 bits, and I know like the ADCs of the microcontrollers themselves aren't very accurate and linear, and you have to worry about reference voltages because they're not inherently precision measurement devices. So they're not naturally good for differential measurements, and they're also limited in range and resolution. So all the things that we don't like. And with regards to input impedance, I haven't actually tried it because it's not just simply like AC input impedance. We care about DC leakage current. So whenever you're looking for specs on a capacitor or on a measurement source, you want to look for DC leakage current. And if you're looking for op amps, an op amp is another way to get high input impedance. If you're looking for op amp, you can look for bias current. That's because what's going to happen is either the capacitor that you're holding the voltage on or you're using to measure the voltage, it's going to drain, or you're going to get or you're going to get bias current, which can even charge up the capacitor, which maybe I'm not sure if you all are aware, but if you do connect a capacitor to the inputs of a op amp, it'll start to saturate. So that's also not ideal. So what's the approach we're taking here? I'm going to be using an Arduino Uno, and I'll share my screen, content from another screen, advanced content from another screen. All right, not the yellow one, this. So I'm using this Arduino. I can't really zoom in there. I can lift it up. Use Arduino here, and this is a external ADC to the Arduino. It's an ADS1115, and I'll be explaining about that. But we're going to use that, and I'll be showing its use. But going back to the whiteboard, so it's pretty well documented online about how to generally set it up. But there's one really important distinction that I will talk about today, which will allow you to get the high input impedance that you would normally not get, although it's listed on the data sheet. So if you look up ADS1115, and I'm using the Adafruit library. So here's, you could just search this information online. You can come up with a lot of information on it. It's easy to hook up. You can also use the Arduino Nano, that also works, or probably any microcontroller. What's so special about using the external ADC? So I'll talk about that right now. So why use the external ADC? So the one reason, okay. So the first reason is it has 16-bit resolution. That's good. And it has its own internal voltage reference. So this is for precise This gives us precise measurements that are referenced, so we don't have to worry about the internal reference voltage of the Arduino anymore, or providing a reference voltage. It makes it really easy to use that. The other thing is that it has differential measurements, so we can measure negative voltage. But be careful here. Negative voltage with respect, not with respect to ground, with respect to the input. And I'll be talking about that more. So this is not globally or universally differential. But if, for example, you have a capacitor at the end, which is not referenced to ground, like we will for our piezo, then you can actually measure true differential without having to worry about its reference to ground. So I'll talk more about that. So differential measurements. And also has many scales, many scales to choose from. It has a built-in amplifier, which is good and bad. So it has all the way up to plus or minus 6 volts to plus or minus I think probably like 200 millivolts. And it's very precise. So it's 16 bits of resolution. I think they're like 32,000 levels versus the Arduino, which has 1,000. So it's probably more than 32,000. I forget how much 16-bit is. Maybe somebody can write it in the chat, but it's a lot. It's very there's a lot of levels. So I've hopefully convinced you that this is worth doing and trying. Here's the data sheet for this, and I want to highlight a couple of things here. Something that are very important to us here is the input impedance. So if you see here, if you use this plus or minus 6.144 volts, you'll get actually an input impedance of 10 mega ohms. Or if you use the lowest scale, which is plus or minus 0.256, you'll get 100 mega ohms of input impedance, which is great, and it'll give us a lot of time for the time constant. If we have a 1 microfarad capacitor and a 100 mega ohm resistor or input impedance, we have now 100 seconds. But if you have 10 or 100 microfarad, it'll just increase even further. So it's very stable for our measurements. Now, none of these things that I mentioned will get us to the stability of the multimeter, the modified multimeter that I showed last time. It won't get you that close. I'm going to show the modified multimeter to be useful to help us understand how good the system actually is or isn't. But I want you, so what common mode input impedance means is it's reference to ground. So one of the analog channels is measuring the capacitor, and the other one is grounded. So it's basically this. So it's analog. So you can say it's the first channel or whatever channel of your ADS1115. Let me just write that. Let's see, this is ADS1115 analog 0, and this bottom one. You could say you're going to reference that to ground. And this is what that's talking about when you have it in that configuration. You'll have those impedance values. But I will show you, because I'm doing a lot of experimental things today, that doesn't end up being very good because it adds bias current. I think they have bias current listed somewhere here. Bias current, micro amp, input leakage. There's bias current basically. So what happens is the capacitor, if you set it to plus or minus 6.1 volts, and you hook up your capacitor is not going to drain back to 0 volts. Like it's going to drain. It's going to keep pumping current into it slowly, so it'll get to 6.1 volts. Even if you have a negative voltage on your capacitor, it'll like remove the negative voltage and slowly start to come up. And that is might be surprising to you. So it has high input impedance, but it doesn't necessarily mean that for your capacitor measurements. Now, here's what we're actually going to do. We're not going to use the mode where we have the common mode where one side is grounded. We're going to use the other, one side is differential. Therefore, we can get the full voltage range. Note that you cannot get the full voltage range. You cannot get a big negative voltage if you use the common mode impedance, because you're limited. So if you use if one side is grounded, so any input cannot be lower than minus point. So the voltage, the supply voltage minus 0.3 volts. So basically, this means negative 0.3 volts is the lowest possible measurement for common mode. So common mode means reference to ground. If any of the inputs are referenced to ground. So basically the capacitor cannot be referenced to ground at all. That's what it means. Because or else you won't be able to use use the full voltage range. So we're going to do differential and differential such that none of the inputs are referenced to ground. In that case, you get in these input impedances. So for the highest scale, you get 22 mega ohms. And as you reduce the scale, the input impedance drops, and that's due to the internal circuitry. So therefore, I'm choosing to use this this scale as 6 volts differential. And it's pretty interesting how the measurement occurs. So basically, whenever a sample is read, there's internal capacitors that are charged. So it's actually not a resistor inside of this there's no resistor like a 10 ohm resistor or a 22 mega ohm resistor inside of the ADS chip. It's actually continuously like charging these little capacitors inside of the chip in order to read the voltage. So because of that reading, so some charge is taken. So what that means is that the more we take measurements, the more charge will be extracted. So this is a key concept here. So the faster the data collection, the lower the more charge is removed from the film capacitor that we're using to measure the piezo preload voltage. So therefore measure this is really important. Measure less. So instead of measuring 100 times a second, measure 1 time a second. Measure 4 times a second. And the other point here is and use small measurement times. So make sure the measurement time is very small and make sure you're not measuring too many times. This will give you the best results in terms of the highest effective input impedance. And we see here 22 mega ohms. And I wrote in my like LinkedIn advertisement that I got 4 giga ohms. So how did I do that? Am I like lying, or am I like doing some type of like acrobatics with the numbers, and I'm just playing it up to get people to think I can make chips do what they can? That's why people hire me. No, it's not that. It's that this input impedance is assuming a certain data rate and continuous collection. Like you're continuously collecting at 128 samples per second. But this, we're actually going to reduce both the samples per second and the time of measurement. And I'll describe how to do that. And let me know if there's any questions. I might be going to a little bit of the details, but I had to learn a lot of the details to make all this work. And this part here, and these page numbers is number 14. It talks about that duty cycle for low power. I don't care about low power. I care about very small collection time. So I'll explain that in here in this one. This area talks about the collection time again. And also it talks about how the voltages are measured. And here's the schematic of the diagram. But maybe I figured everything out, so you may not have to. So initially I came with this idea. So when I didn't know as much about this chip, I came with this idea that I want to use a 10 microfarad capacitor. So this is my initial idea. And this webinar might end up being longer than I intended because I'm just explaining everything I learned, because that's what I like to do. But so feel free to jump off if you need to, say bye or don't say bye. It's up to you. But yeah, I appreciate you coming so far. So my initial approach, use common mode. I want to use the common mode voltage, plus or minus 6 volt range, to get the 30. I think it was what was it here? So the plus or minus 6 volt range gets me 10 mega ohms, but actually I wanted to use the plus or minus 250 millivolt. So I wanted to use the plus or minus 0.25 6 volt range to get 100 mega ohms, not milliohms, that's not good, mega ohms of input impedance, and a 100 microfarad capacitor. That would get me voltages usually, so the measuring voltage would likely be between that, would fall in the range, and I'd have a good impedance, as a good time constant, basically. But what happened here, when you use the common mode value with the ADS device, what happens is that the capacitor saturates. So when you connect, and I'll go back to this. I should probably just copy this. So when I went here and I connected, I'll use the pen tool. So here's A1, right? So I connected A1 to here. I'll just use red. That makes more sense if the red's gonna work. Yeah, red's gonna work. And then I use for ground, I actually connected this part to ground, which was here. So I just connected that, and my head's in the way. I connected here. But what happened was, if I show voltage measured over time, like if I use my charge capacitor method where I charge up a capacitor on a battery just to get it to work. So basically, let's say you preload to 0.2 volts, right? So you preload here, but what happens is that slowly over time, the circuit charges A0. So A0 saturates at 0.256. So you didn't get away from a negative time constant. Now you got like some positives, like linearly increasing voltage due to bias current, so there's not leakage. So there is that 100 mega ohm input impedance, but that puts a huge bias current on the system. So by using a smaller range, I didn't get away from this value. I didn't get that 100 mega ohm input impedance that I wanted to, because my configuration was not such that would happen. I actually got current coming in. And if I have time, I'll show that. So I wanted to use the smallest range because I would actually be able to measure negative voltage, because as I mentioned, and it also shows in the data sheet, the lowest voltage you can measure using common mode impedance. Like if you have A0, the lowest it can be is negative 0.3 if you're using it reference to ground. You can't have it any lower than that, and that's why I use the smallest range, and I got the biggest capacitor that's conveniently available for film capacitors. But that didn't work because it's saturated. And when I went to when I tried the other ranges, like I tried plus or minus 6 volts, and that was a 10 mega ohm range. So it's very similar to our multimeter that also saturated. So everything's saturating here, but it's going slowly. But the whole point of this exercise is I want things to be very stable. So I don't want them to decay or drift high. So basically, if we talk about common mode impedance, the common mode, and I'm talking a lot of specifics about this chip that I'm using, but I think it applies to any one. So common mode measurement of a film capacitor used for common mode measurement of a film capacitor used for preload measurement. I don't, this is no good, basically. There's basically drift high. and I found that to be annoying because still we could use that multimeter and use it 100 microfarad, but it slowly decreases in voltage. But I want it to be very stable, similar to like a tera ohm or very stable, perhaps much more expensive equipment. I'm not trying to do shortcuts or say, oh well, it doesn't only takes 10 seconds or 5 seconds to preload, so who cares? Like, as an engineer, I don't like seeing like numbers droop when they shouldn't. So I had to rethink it, and I had to get into a lot of um a lot more troubleshooting. So what I did, and I found that the differential mode for this ADS for the ADS chip, and I probably should retitle my presentation to also include the chip because I'm talking a lot of specifics about it. Basically, the ADS1115 common mode has a drift current, I guess, or bias current, which will saturate the capacitor. So even after you short it, yeah. So what happens is that I'll describe it. There's a comment here. Saturate the capacitor. Uh, However, the differential mode does not saturate, and that's what I found. Such it acts like a kind of like the resistor um input, like a multimeter. Because if you notice from a multimeter, no matter if you load it with a negative voltage or a positive voltage on that capacitor, it will drain back to zero. Um, so somebody wrote in the comments, you can write the code of the microcontroller such that it can save the increase in voltage and not the absolute value, so the leakage will not be important until we untighten the bolt. So that's true. So you can write the code, because if you know that, and let me just draw these lines. So if you have this, and there's another problem here, sort of. So I'd like to make as um little correction as possible, or else like why not use then somebody's going to say, well, we should just use a official device or something. So what I mentioned is this is how the preload's going to look. It's going to go like this, and it's going to then it's going to actually over a decent amount of time, so it'll take a long time to start to saturate. So this is your preload time, this is time, this is voltage, this is the time you're preloading, this is the time when nothing's happening really. So it'll slowly, and this is the max range. So it'll saturate to here, and if you untorque it, it'll then come back from this point. And you could do some calculations like, well, I'll minus however long it takes. However long I'm measuring, I'll subtract that voltage. But if you have any errors, that errors are cumulative. So it integrates, the error integrates. So if you add a correction factor, great, but if the correction factor is off or even too high, maybe for some cases, it'll continue to integrate. And that's the nice thing about having a capacitor, because the capacitor does all your integration for you. You don't have to worry about bias current, but in this case, you do. So I did not like that, although the drift isn't very fast, especially for the lowest range, it's the fastest, but for the highest range, it's not very fast for the common mode, but it's it was faster than I was comfortable with, and I'll try to short if I can. So the differential mode does not saturate. And the best differential mode, and I won't go back to the data sheet, but I remember it by now. I've kind of looked at it so many times. So at plus or minus 6 volts, we have 20 mega ohms for the differential case, and we also, and that, so because the voltage is higher, I decided, hey, why don't we use a 10 microfarad capacitor, because we're going to have about 0.2 millivolts of resolution, and a few of those, there'll be some noise in the mixture too. So we can at least get a larger voltage, and yeah, it won't be as nice as a 100 microfarad capacitor, but so this will be just be a little bit better than the multimeter. And I'll remind you that the multimeter with 10 microfarad capacitor with the 10 mega ohm multimeter, it drops very fast, and it's not, I'm talking about the comfort level or that level of like uh research, I don't know, integrity of your instrument, that your instrument doesn't have an inherent issue, like a really large inherent issue with the measurement, like it's going to start like time difference, and then we'll talk about manufacturing and some how fast you do it. And whenever you get into your troubleshooting meeting for your transducer, you're always talking about, oh, how long did it take you to preload, and what was all of this about. And you could use the max range function. Somebody mentioned that in one of my YouTube comments, but still, that's a band-aid for the actual issue, which is, why do we need the voltage to decay? Is there a way around that, besides, one is to buy a more expensive instrument, or is there another way we can handle this? So this also I was not happy with it. If I use 100 microfarads, the voltage would be too small and it wouldn't have enough resolution. And I'm actually thinking from the perspective of like selling this type of product. Like, I would not be comfortable buying this kind of product it's not good enough, basically. And especially when you get into lower voltage ranges, we don't have a multimeter, but now we're doing our own filtering and everything. And if I hold the terminals, it'll start to charge up a little bit. So if we have like a millivolt or 2 millivolts of error or something like that, that's gonna end up being unacceptable completely. Because the 100 microfarad with the small transducer end up being like 20 millivolts of preload voltage. If I have like 3 millivolts of error by like touching it, or some things like that could happen, it's too much. I can't trust such an instrument. Uh, so now what am I gonna do? This is not gonna work either. This is gonna be too fast. Do I need to like do some integration? So the answer is no. The answer is what I talked about, the data sheet. Uh, so the data sheet, it told me that the input impedance is actually not a real input impedance. It's basically the sampling of the capacitors. So we can do two things here. So the first thing I did is, you can set the samples per second, so to 860 samples per second. Now and this actually reduces. So let's just say the measurement time is now 1 millisecond measurement time. So the measurement time is reduced, but hey, now we're like measuring it more, so it doesn't even matter. And the second is that only do a measurement once every 250 milliseconds. So now I completely change everything around, and I'm measuring for 1 millisecond every 250 milliseconds. So that's like for 4 milliseconds, I'm actually doing sampling. So those internal capacitors are probably like picofarad range. They're being emptied out, and they're constantly being charged and discharged. So it's happening only like 4 times, and for a short period. Therefore, I was able to get 4 gigaohms. So with the modified multimeter, and this is kind of jumping ahead a teeny bit. So with the modified multimeter, these are seconds, and this is voltage. So I'm measuring this from the modified multimeter. So with the Arduino hooked up, so I started with 238.9 seconds, 9 volts, millivolts, and what is it? 60 seconds later, it was at 238.5. So that is I think I had to have a time constant of 40,000 seconds, which for my 1 microfarad capacitor ended up being 4 gigaohms. So that is good. I like that. That's stable enough. I'm comfortable with that. I might even, I wouldn't even be comfortable selling that as a product. Like, this is stable enough that I can consider this as a good research instrument. It's not going to be, who cares about 3 or 4 millivolts in this range? It's not a big deal, in terms of the whole range of measurement. It's very accurate now. But how do we do that? And also, how do we code it in? And there's one really big, important issue that is not listed on any kind of online resource. So I'd like to provide that as well. the one thing I want to highlight is in this circuit here. And this is like this is what I did this, I think last weekend. I figured out how to do this, but then I forgot the trick, and then I went crazy yesterday and I remembered it, or I fooled around and I probably do the same process. I came back to the solution. So I'm doing a differential measurement, A between A0 and A1, with the plus or minus 6 volts range, which is great. And I'm going to use a 10 microfarad capacitor, and I'm using 860 samples per second, but take a reading, or call for a reading every 4 times a second. So it's but this still ended up dropping the voltage very quickly, even when I hooked it up like this. And that was severely annoying, finding the data, kind of the data sheet not really working. What's going on? There's still some type of interaction between voltage drop or voltage drain and the circuit. And if you go back to the data sheet here, you will, let me go back to the differential. Like these two inputs, this is representing the differential measure. These two inputs are referenced to ground, and in kind of a way, so there's some type of charging going on, and this all dropped the voltage very quickly, and man, the time is running out quickly, so sorry about that. But this all didn't work either. So what I ended up discovering is, connecting a low value film capacitor. And let me just measure it right now because I have it installed. I don't want to not have it for you. I have everything right here. So that film capacitor is 1.6 nanofarads, 1.46 nanofarads, between A1 and ground. And I think that that gives a place for that discharge current to go. And I haven't thought exactly about why this is stabilizing the voltage, but because I'm using the modified multimeter, I can verify it. So that's another reason for using the modified multimeter, or making one if you don't have one, is it can be used. So the modified multimeter can be used to verify other setups, even though it's in and of itself it's a little bit too crude. It can be used to verify other setups, so that's why it's extremely useful too. So as a kind of a verification tool that you built the circuit, that's good. And the voltages that you're measuring from your Arduino are actually reasonable and large enough. That's another reason why you want to have the modified multimeter that I showed in the last webinar. So I guess without further ado, I'll be sharing the code, and the code will be in the probably in the comments of the YouTube video. And this is the circuit diagram, is the same as I guess I'll just draw the circuit diagram here. So this for the circuit diagram, this is A0, and I'll just delete that. This is going to be A1 here. A1, but A1 is connected to ground with a capacitor. So I'll just draw a little box maybe. So 1.5 nanofarad. Okay, it's not really right in there. So we have 1.9 nanofarad. Please move. Okay, you're not moving. Between ground and this 1 nanofarad. So this goes there, and this goes to ground. That stabilizes the voltage. So it droops. The voltage basically drops, and that's the nice thing. It always goes in one direction, so it always goes back to 0. I'm also okay with that. I'm not okay with it drifting to like saturation. Then I have to account for the max voltage being hit, but it's kind of slowly drifting back down to 0. that's fine, especially for that kind of value. And in any realistic time frame, this will not, if I was converting this to megapascals, I would not even be losing like 0.1. If I was like 60 megapascals, I would not hardly be losing 0.1 or 0.2 megapascals from that, which is not significant. So I hope I provided everything in order to build a circuit, and I'm using the basic schematic and setup here. So let me go ahead and share my screen. Uh, so I think what I want to do is I'll share the setup and what I have. New share, advanced content from second camera. Or maybe even better, I will just share the Arduino screen. Um, I don't think it's up yet. Okay, so open the Arduino screen, and it should come up. 1 second. Share, new share, and yeah, here's Arduino screen. So I'll share the Arduino screen, and I'll change my video to the virtual to the setup here. Okay. Oh, it's like blurring it. Okay, let's not do the blurry thing. Let me change that. Video setting. Uh, blur. Okay, remove the blur. Blur my background. Okay. Is the video big enough? Can you see what's going on there? Or maybe I need to make it bigger. Uh, Let me make it bigger at first. Or I guess if I stop let me stop the video and I'll share my I'll just share that so you can just see the big version up front. Um, content from second camera share. Uh, okay. So this is the setup. It's a bit crude. Yeah, but please ask questions. So this is just everything connected through Arduino like normal. These wires aren't doing anything. Um, I actually have this. I have honestly two 10 microfarad capacitors. One is actually just, I'll just take this off. So this one right here is the one that I would have doing the measurements. This one right here. And this is then connected to, right, A0 and A1. Don't want them to touch here. And I'll probably have to double check that. And then the trick here that I mentioned is that this capacitor needs to go between ground, which is the second pin there, and probably any of the leads, but I put it on A1. And that's my exact configuration. Actually, it needs to go one over. If anybody can see that here, and A1. And I think I can zoom in on here. I think I can zoom in there. So just to give you all an idea of what that's all about. Okay. This is not even doing anything. And then I have the modified multimeter. I also have this LCR meter if we need to see anything there. But I can turn this on. And it's already charged up, so I'm probably gonna discharge it or whatever. But this is a setup, and I use this modified multimeter. I guess I don't have to have this other capacitor, but I just have it on there, so I'll just leave it. So I'm just actually connecting it to this, and these here are the measurements. And right now, I just want to see if I have. So right now the measurements are going on. So the Arduino system is on. You'll have to just trust me on that. And then I'll just connect this. So this will actually just help us to see the voltages, which are there. We will see that this value, I can make this larger a little bit. They are dropping. What I do here, just for like testing methods, I will get that battery, which I had somewhere here. Well, I do have a, you could say a voltage source on my Arduino. How about that? I'll just charge it up using that. And when I take it off, it won't be there anymore. So I could Well, and this doesn't actually make any sense because I hooked itself up to its butt. I do that. Okay. All right. So, all right. So let me just put this back. It gets kind of confusing when all the leads look the same. So I'm just setting it up just so I could see the voltage drop, and I just want to show one part at a time so I don't get too confused here. So this is that. And I could put this on here. I charge it up using 3.3 volts. Now it's a negative. So there, I'll just stick this here somewhere. So you can see the voltage drop. So it's actually doing the readings right now on the Arduino too. You can't see it obviously, but it's doing the measurements there. And I'm actually going to go to the other screen now. So this is negative, and also we're working in the positive direction. So look, watch what happens when I take this capacitor out. Whew, it's going fast. Like that's what like, oh my God, then I really got to do some type of like integration work. But this is something that I have not found anywhere that why this should work. Now you could put resistors and things in here, but that will increase noise. Whenever you reduce the signal, you increase noise. So I'm gonna start sharing. I'm gonna share the Arduino screen, and I have another. Actually, I'll just share screen 2 in general. So I'm sharing the whole screen now, and I'm going to move this like that. Okay. Um, and I want to go to just view. I'll just get rid of all these. So you can see it. So this is the live view. I forgot how to get rid of all this bottom stuff, but that's fine. So it says 19.2 volts, and this is you can see on Arduino it's 19.2. This is negative and positive. But you guys won't hate me for doing that. Then if I get this again, so this is like if I preloaded it, then this would be the same kind of effect. And then I have this and you can't really see the Arduino that well. I mean so this is that. So this should increase or something. Yeah, now it's negative 133. Um, and we also need to show that it goes positive. So I think this is not that big of big text. I don't know how to increase the text size. So obviously if you can export it using the serial monitor, you can do it in other ways too. So I guess I'm not going to go too much farther into it, but I will I'm just gonna go ahead and reverse this direction here, just to show that you can measure negative voltage. So I'm just going to reverse reverse the direction of these of how the leads are interfacing here, so we get the same. I think I touched something, therefore it went to 0, and I can tell that's true because I always have this modified multimeter on there. So let me just recharge this capacitor, and I'll just show the code. I'll walk through the main parts of the code, and I'll also be uploading it too, so you can have that. And you should have, I think, absolutely no problem um, doing this exact thing. Oh, now it should go positive. That's good. And then so yeah, it works. It works pretty well. I don't know the extent of how if I think the full range should be able to be used. The one of the channels is floated. Now, if you see this is negative now. I can make it bigger, but I don't really know. And if you want to look at the over time, what's happening. Uh, so I can go through. So does anyone have any questions so far? I'm going to go through the code, and then I'll be done for the day, I guess. But okay. So here's the code. Can you view increase the size? Is there a way to increase the size of the text preferences? Editor size font 30? That would be sounds pretty big. Okay, here we go. So this is the basic Adafruit library. This is the extra thing that's like this is also a code, but it's not potentially obvious to somebody who doesn't dig into kind of definitions sheet. So if you install this library, which is pretty standard, most tutorials talk about it, then you have to put this code in here for 80 seconds, 860 samples per second, reducing the sample time. This here talks about that you don't want to measure negative voltage or too much positive. This is the different ways to set the gain to select different voltage ranges. So this is part of the standard code. And selecting the largest voltage range is the works well. And I think it's good for the selecting the largest voltage ranges. It works good for the input impedance. It's the highest input impedance for the differential mode anyways. Otherwise it'll drop faster. And then here, this is the normal code where you have the single-ended reading. That's common mode, basically reference to ground. So one of the sides has to be at ground. This is differential mode. So I'm doing something kind of useful, that one side is reference to ground through a capacitor, which I think takes care of a lot of the leakage current. But now we only get the true true impedance differential kind of, and because of the lower sampling rate and the higher sampling rate and the lower sampling lower sampling time and the lower sampling rate, I'm able to achieve that 4 gigaohms that I spoke about. Let's see. So here, this collects the voltage or the ADC value, some 32,000 up to that, negative or positive. This standard code as well, it converts it to the voltage according to whatever gain setting you did. Here is a running average of 10 samples. This will allow you to get much more accuracy. It's obviously something you can have control over, that you can do here. And let's see here. And this is prints the voltage in. I multiply by 1,000. And this code here works with the at running the average, that if you go over 9, if we start populating the array that's using the running average from the beginning. So I could just probably put that there just to keep all of the code that goes with the running average together. And just prints it out. And obviously you could do any type of code now. And let me just pause my screen share, and it's probably obvious to many of you how you would input the voltage values. Basically how you would. You're not seeing what I'm trying to get to right now. I'm just trying to get to the calculator that I have online, but I'm going to show you how you would put the calculator here. But any of you can leave right now. If you have any questions, please go ahead and ask. I'm going to upload the code and you can leave, but I'm just going to finish writing the calculator for it. And therefore it'll output to megapascals. Again, I kind of like when people do things live, because otherwise, like, you don't, I don't put everything. Sometimes things are missed. So I will just have this there, and I'll resume the share. So I guess we could put it, and maybe I'm doing a kind of boring coding that I'm not really that good at, but I'm going to do it anyway because I can. So if we have, we have the float OD ID, the inner diameter of the ring. What else do we have? We need to know the desired pre-stress, which we don't really need to know the desired pre-stress here, unless you want to have like an alarm. So you have to have, you need to know the D33, N extals, the number of crystals, and the capacitance. So capacitance, I'll just write that. So on my online example, I have an OD of OD equals 40 millimeters, and I have the ID on my online thing equals 20 millimeters, and the D33 equals 245, and that's e to the minus 12, but I'll save you the minus 12 for now. And then the capacitor. So right now, the capacitance, that's going to equal 100 microfarads or 10 microfarads, or right now it's 20. But I'll just write 20. Um, so the area is equal to let's see, 3.1. This is kind of the boring part. Sorry, guys. 1415 6 multiplied by OD times OD minus ID times ID, or pi r squared, and then you divide that by 4 here, and then the force is C3. I'm looking at the force D33 times well, the force is the pre-stress. We don't need to know that. Sorry, the C3. So we don't need to know the force. So with the charge, what's the charge? The Q. The charge that we're looking at is, I guess, the charge needed for loading. So how do we get to the stress? So the stress is the force over the area. So the force is equal to D33 multiplied by the charge, and the charge is Q equals CV. So capacitance times the voltage. And the voltage is determined by what we measure here. So and the stress is equal to the area, or the force, divided by the area. So these two things will be reiterated. So I'll put these down here. And I don't think I put those in here. We might as well declare them. And that will give you the force in pascals. As long as I put the capacitance in microfarads, the output should be megapascals, I believe, instead of pascals themselves. So let's cut that out, and let's put this right here. This is just showing basic coding too. So that should work there. And D33, again, I guess I should probably put the e to the minus 12 on there. I don't know how it's going to handle that in here. I don't think you can have so many values. But let's just see how it turns out. I can change it from my calculator later. Okay, so that's the stress divided by the force over area. I probably should E force equal, probably multiply by 1, e to the minus 6, because the capacitance is microfarads. The D33 is in picometers. That's negative 12. Anyways, I'll figure that out and make sure it works first. So what you want to do, I'll modify this, and yeah, I know this is a little bit boring, but you may leave if you like to. So I'll put stress there, and then serial print. I'm just, because when you have to manually kind of put all the things in here. So all by M P A, and I'll put comma, space. So that's going to print this, and I'll just use 1 digit for that, and I'll kind of know how much to divide it by in the end. And then I'll have to put a semicolon there and print voltages. That'll be the volts. So I'll just copy this, put that there. This ln creates a new line, so I'll do the new line at the end, and I'll just write, this is the number of millivolts. I'm wondering, this is gonna just be fine. OD does not name a type. Didn't I say float? Yeah, there's some. Oh, here it is. Stress divided by F area. Did I didn't define area here? Okay, area. Oh, anyway, so I'll put this in the end, but basically the code from before worked. I'll make sure I just put that in there. This is the basic steps. And yeah. So do you have any? So let me stop the share. This is just a funny thing. Also, I'll have that in the comments about my video and actually whoa, this camera here. Yeah, do you have any questions? I'll just finish that up. I don't think there's a need for you all to wait around.